Evening, everybody. 5 o'clock on Thursday night. So, you know what that means? Time for some Calc 3. Um, like last time, let me know if you have any issues hearing me, if the mic seems to be cutting out. If I don't hear anything from you, I'll assume it's uh, good as normal. But, I know it got a little staticky last time. So keep me posted if anything like that happens. All right, let's talk about where we're at, where we're heading, and then we'll get into it. So we're starting module 3 today, and now we're really going to start to get into the meat of Calculus 3. We're going to start off today talking about functions of 2 or more variables, because that's what we're going to be doing calculus on starting next week. So we're really going to start to get into some interesting topics. Things like tangent planes, optimization, directional derivatives. So we're going to get into some really cool stuff over the next few weeks. But we need to start somewhere, and we need to start talking about functions of 2 or more variables. We've talked about these a little bit actually already. For instance, we've talked about planes, right? That's a linear function in 3D. And we saw that, it might have the form of maybe f of xy equals mx plus ny plus some constant. Okay? So we've already started looking at planes in 3D. Those are our linear functions. Now we're going to start to expand that. And what I want to do today is show you some plots, just a few, and some concepts that go along with 3D plots that I think will be pretty intuitive for you, so that you can go forward and start to identify 3D plots and some of their characteristics. So let's go ahead and dive in. So if you remember back from your algebra days, if f is a function and y equals f of x, that allows us to draw a plot. In other words, for an input x, we get some output y. And it gives us something that we can, plot on a xy plane. So that would be our curve of y equals f of x. And we can think of each point on that line as being some xy plane. For every input, we get a unique output. If you remember, we know a graph is a function because it passes the vertical line test. So, for instance, a circle is not given by a single function in terms of x and y, because a vertical line would hit it in more than one spot. All right. We have a very similar restriction in 3 space, and we'll talk about that. Now, we know there's ways around it. Parametric equations, right, can give us a circle. Polar equations that we talked about a little bit about last time can give us a circle. And those can be done, polar can be done as a function. But in terms of our rectangular coordinates, we have a unique input giving us a unique output. So a circle wouldn't be necessarily the graph of a function. So again, we think of our graph as a set of ordered pairs. Now, we need to start thinking in terms of 3D. And that's that a function may have more than one input. Now we're starting to get, what we do with math is we start off with a single input and a single output because it simplifies things. We have 2 dimensions. It's easier to draw the graphs. It's easier to get out a lot of the characteristics. Then we start to expand, but we see that a lot of the things still hold, like our definition of a function. But the amount of money in a bank account depends on both interest rate and time. So the balance at any given time is a function of 2 variables, the rate and the time. The height of a ball thrown upwards depends on the time since it's been thrown and the initial velocity with which it was thrown. So the height could be thought of as a function of those 2 variables. If we change either of those variables or both of those variables, we get a different height. So there's a lot of real world examples that we can think of a function having more than one input and giving a unique output. These are just a couple of examples. So in 3D, if we're going to call f a function, we're going to let z be some function of x and y. So now instead of having an ordered pair, our graph is made up of ordered triples. But it does give us the ability to plot it. Z can be thought of as the height above or below the xy plane. So let's talk about plotting a point in a 3D coordinate system. I'm not going to draw this. We're going to go ahead and use our plotter. So if we wanted to plot the point 3, 5, 7, here it is up here in blue. All right. And what we can see is if we look directly down the XY axis, so let's see. Notice that that point is at 3, 5. And then what z does, what the function does is it projects it to some level, in this case 7, above the XY plane. So we can start thinking of functions of two variables as being the height above or below the XY plane. That's what that output is giving us. Now, the reason we think about it like that is to draw the analogy between 3D and 2D, where in 2D, our single input x gives us the height above the x-axis. Now, our ordered pair is giving us the height above the XY plane, all right? So I really want to keep the connection between what you guys have done in algebra and Calc 1 to what we're doing now, because all the relationships hold. And that's what's really cool about a lot of this stuff. We're going to find that a lot of the stuff we were able to do before still holds. It just looks a little different now that we're in 3D. Now, let's start to look at some functions. So if f of xy equals x squared plus y squared. Now we're going to plot this, just not right away. Because if we didn't have a 3D plotting system, we need to have a way of figuring out at least an idea of what the plot would look like. So what we do is we start by looking in either the xz plane or the yz plane. So if we set y to 0, what we're essentially doing is looking in the xz plane. And if we go ahead and set that to 0, then what we have, our function simplifies down to z just equals, if y equals 0, z equals x squared. And that's something that, without any technology, we can plot in the xz plane because it's a curve we've seen before, which is just our standard parabola going through 0, 0 with a vertex at 0, 0. X, this would be our z. We could also do the same thing by setting x to 0. If we set x equal to 0, let's make a little note that that's where we set y equal to 0. We get z equals y squared. We'd get almost the exact same plot, except it'd be in the yz plane. These are called cross sections of our graph. The way we get a cross section is by setting one of our input variables to 0, because that puts us in the plane of the other two variables, and it gives us a 2D image. The reason that's valuable is we've got experience drawing graphs in 2D. Drawing graphs in 3D is not simple. So one of the ways we simplify the process is by looking at the cross sections of a function of two variables. Now, what we're seeing is, okay, we got a parabola in the xz plane, we got a parabola in the yz plane. You can probably already start to imagine what the 3D graph looks like. It's this bowl-shaped graph. which is called a paraboloid. Here, let's turn up the grid lines, make that look a little smoother. There. And again, if we look down any set of axes, if we look down, for instance, the XY, we see that parabola structure. Same thing if we look down the XZ, we see that parabolic structure. If we look down the YZ, we see the parabolic structure. Yes, satellite dishes are paraboloids. So satellite dishes are something that are parabolic because of the way the waves reflect off the edges. And another thing, as we talk about these cross sections, we can also set our output to 0 or our output to different values, 0, 1, 2, and that creates circles. They reflect to a certain point. We're not, you're right, we're not quite covering that in this class, Garrett, but yeah, that's why that's why satellites are parabolas, because they reflect off the sides towards a certain point called the focus. And if we look directly down the z-axis, we see that circle centered at 0, 0, which we can see is the x squared plus y squared. Yes. Yeah, kind of like the satellite on the Death Star. If you remember how for those of you who like Star Wars like I do, if you remember how the Death Star fires, the laser meets at a certain point and then goes, that would be the focus of that paraboloid. All right. So paraboloids are something we'll see every once in a while. We're going to come back to this graph a little later. But there's going to be a lot of things that we can look at in graphs or in functions to kind of identify what the graph is going to do. So here's the graph of e to the negative x squared plus y squared. This also, our paraboloid also had an x squared plus y squared in it. Something to notice about those is they have what we call like a circular symmetry, because we can think of that x squared plus y squared as equaling r squared. And if you remember, this is very similar to polar. And it simplifies our formula because the value of the function is the same at any point on one of these circles. So here's a kind of a nice drawing of the circles. Any of these circles are the same z value or the same height above, or if it opens downwards, below the xy plane. So this is referred to as circular symmetry, and you would recognize it in a function because you see an x squared plus y squared component. All right? That might be a hint that the graph might be easier to do in polar, is seeing that x squared plus y squared. If it's got an x squared plus y squared plus z squared, it might have a spherical shape to it from our spherical coordinates of last time. Now, again, what I'm trying to do is, there's too many possibilities of 3D graphs for me to go over all of them. I'm just trying to give you some stuff that you could look at to kind of get an idea of what a 3D plot might look like. I'm not expecting you to memorize them. We're going to have the 3D plotter for most of the work we do, but we want to have a way of reconciling a function with its 3D surface. So let's talk about this function here. F of xy equals the square root of 4 minus x squared minus y squared. All right, I've got this one put in here. Let's make that a little smoother. And I'm going to zoom in on it a little, but I think you can already kind of see the shape there. Where is mine? Oh, there we go. It's moving a little slow. There we go. All right, notice what we have for our object here. We have basically a half a sphere. What is just asking what it looks like on Calc Plot 3D? Sorry, I'm not sure.
The example question.
Well, some of these, we need to be able to identify what they look like even from the function. And that's what we're doing. We're reconciling the function with what it looks like in the plot. And so what I'm going to do is go through and kind of give you ways of doing that without necessarily having to be able to plot it, to already have an idea of what it looks like. So, I've already plotted this one, so we know what it looks like. It's a half sphere. But there's specific reasons why it looks like a half a sphere. And that's what we want to talk about. A couple things that we can note about this one. And the first thing is, if I were to square both sides, notice I would get z squared equals 4 minus x squared minus y squared. And if I add the x squared and y squared to the other sides, I get x squared plus y squared plus z squared equals 4. This would be the equation of a sphere with a radius of 2. That just comes from our distance formula. All the points are equidistant from the origin. Now, there's a very specific reason why we only get the top half of a sphere. Notice the square root. We're not going to be able to get any negative z values. That's why we're not seeing this bottom half of the sphere here. That's okay, because if we had the bottom half of the sphere, then this would not be a function because it would not pass the vertical line test, because a vertical line would hit the sphere at 2 points. So again, this is a connection to our 2D calculus. So that's one way of starting to identify the graph without having to plot it in the 3D plotter. The other thing we could do that we talked about earlier is we could look at the cross sections. For instance, if I set y equal to 0, this equation just becomes z equals square root of 4 minus x squared. That's something we can plot in the xz plane, which is that half circle of radius 2. So, again, one of my goals today is to try and get you to this point where, you're not going to know every single function. We can make some pretty messy functions of 2 variables, and we're not going to know what the plot looks like. But things like paraboloids and spheres, we want to start to get to be able to say, oh, I have an idea of what this is going to look like. Now, the next thing I want to talk about, and this is another way of dealing with 3D curves in 2D. So we have our function. We're going to stick with the same function. We're going to stick with the square root. Oops. This is still dealing with z equals square root of 4 minus x squared minus y squared. Now, what we can do is we can set z to be particular values, because that's something that can be plotted in 2D. So maybe we set z equal to 0. And so there we get 4 minus x squared minus y squared. We square both sides, add the x squared and y squared over. We get x squared plus y squared equals 4. That's a circle of radius 2. Where is it happening? When z equals 0. So that would be in the xy plane. So that's that circle that's at the base of our sphere. We could do 1. So 1 equals square root of 4 minus x squared minus y squared. Square both sides. We're going to bring the x squared and y squared over, and I'm going to bring the 1 over to this side. That would give x squared plus y squared equals 3. So that's a circle of radius square root of 3. But where is it happening? It's happening where z is equal to 1. So that would be a circle. If I wanted to draw it on here, it'd be kind of up here where z is 1. And we could do one where z is 2. We'd get a smaller circle. Now on this one, we can only go up to z equals 2. Anything higher than that, it's going to be off of our half sphere here. But these create a 2D image of a 3D curve. And we have a name for these. These are called contour lines or level curves. All right. These are really going to be really useful for us. What they are is a 2D representation of a 3D curve. And, you know, if you've ever looked at a topographical map, that's exactly what they are. Now, if you ever want to add level curves, see this little button here? It's a little displaced on mine because I've got my window scrunched horizontally a little bit. But that's what's going to allow us to put on level curves. So we'll do one at 0. And we'll do them every, let's do a few of them, make it look kind of cool. Every 0.25. And so that would give us a total of 8 level curves, and we'll do them in red. And then we create our contour plot. What this is the 2D topographical image of our 3D plot. You can see the big circle out there when z is 0. And they even got the z values on the contour line. So when z is 0, we got the far out one. When z is 0.25, when z is 0.75, 1.25, 1.5. Here's a way of thinking of those. Think of these as elevations. So maybe we're looking at a mountain. And these are the elevations of each of these levels, hence the name level curves. Again, contour lines and level curves are used kind of interchangeably. And this is kind of cool. If you actually take the graph and grab it, you actually get it. Sorry, this is moving real slow for me today for some reason. You can see how it puts the level curves on the 3D surface. So level curves, guys, those are just like a topographical map. In fact, here's a topographical map. Now, something very interesting going on when we have these concentric circular shapes. As we saw here, when we had the concentric circles, it led to a peak or a maximum. This is going to lead right into maximums and minimums that we're going to do either next week or the week after. So we were expecting either a max or a min in the middle of each of these circles. These could be mountains or they could be valleys. So here's the 3D map of our topographical map. And you can see the level curves on here correspond to the level curves on here. So those are what level curves are. What I think is really great about this is you guys have dealt with level curves before. Anytime you've looked at a map and they've got different elevations, whether they do them in different colors, they usually break them up with lines, which are your level curves. This is actually not a new idea for us. Now we're going to add some calculus to it, some of the things we know to make this more useful for us. So, a couple things about contour lines, and we'll make sense of all of these. They separate lower elevations from higher elevations. And the closer they are to each other, so think of our circle here, like notice how they're closer together where the circle is steeper. Here, as we get towards the top, they're further apart, or you can see it here on the contour plot. See how close they are together where the side of the circle is steep. Farther they are, the more shallow. The closer they are, the more steeply the surface inclines or declines if it's going down. So We expect a higher rate of change if level curves are closer together. Lower rate of change if they're further apart. Magnitude. Contour lines are level curves. I'll use those terms interchangeably. You'll see them used interchangeably when you go through videos and all sorts of Calc 3 material. So it's just better for us to be familiar with both terms. All the points on any given contour line are at the same height. All right. We can kind of see that here, and we can see it in our topographical map, right? If we're on this contour line, we're at 1,500 feet, okay? Contour lines corresponding to different elevations can never cross. Let's think about why that is. If they crossed, then we would have two heights at the same input, and we would not have a function because every input, every ordered pair from the XY plane has to have a unique output. So contour lines corresponding to different elevations cannot cross. And we looked at our contour plot for our function here. Again, contour plot, level curve. I really do use those interchangeably. All right. Questions at this point? I know I've been talking for a while about contour lines. We're going to talk a little bit more about them here, but anything that and you know how to take you got the Calc 3D plotter, so you guys can look at both the 3D function and its contour plots. By all means, play around with that. I'm not going to worry about this. This is just the definition of a contour plot. Here's what I want to talk about is this is going to serve us going forward. We want to start talking about moving in a direction tangent to a level curve, all right? Remember that if we're moving tangentially, we're talking about that instantaneous rate of change. So as long as we're moving tangent to a level curve, the height doesn't change. I really want to bring a couple of these points home because next week, when we start doing directional derivatives, we're going to apply these same concepts. When I'm saying the height doesn't change, I'm saying the output doesn't change. That means we got a rate of change of 0. So we want to connect this idea of rate of change being 0 to the tangent line or moving tangent to the level curve, because eventually we're going to start talking about derivatives, which we use to find tangent lines. So as long as we're going in a direction that is tangent to the level curve, our height doesn't change. Now, if our path is perpendicular to the level curve, as we can kind of see from our drawing here, that's when we're going to change elevation the quickest. We can see it on our circle too. If we want to get from this contour plot to this contour plot, the fastest distance is a perpendicular line. Remember, we talked a little bit about this before when we were doing the shortest distance from a point to a plane. We wanted something that was perpendicular to the plane. If we want to move from a level curve to another level curve, if we want to change heights or we want to change output values as quickly as possible, we want to move in a direction that is perpendicular to our level curves. Now, if we're going up, in other words, if our z value is increasing, it's called the path of steepest ascent. If the z value is decreasing, it's called the path of steepest descent. So, and we can combine these two ideas because a direction perpendicular to the level curve is also perpendicular to the tangent line. And we know something about vectors when they're perpendicular, their dot product is 0. All these ideas are going to come together next week when we start looking at directional derivatives. So right now what we're doing is we're introducing ourselves to 3D plots and building an intuitive sense of the calculus of how we do rates of change. Next week, And the week after, we're going to look at the mechanical of how we do the rates of change using our calculus tools. It's really cool stuff the way this builds. All right. I'm just going to talk about this real briefly. Level curves of linear functions. So linear functions are our planes. Their level curves are actually pretty easy to recognize. Let me get that drawing off of there. So that's, whoa, stop spinning on me. All right, here's our, so here's our plane. And if I were to add level curves to this guy, we're going to space them out a little bit more. And let's start them at a negative. Notice what the level curves look like. They're all lines and they're all parallel. Because what we're doing is we're setting the z to be a constant, and all that creates are linear functions in the xy plane that all have the same slope. So if you have a plane, we know that its level curves are going to be parallel lines. If you have a plot of level curves or a contour plot of parallel lines, we know the graph is a plane. And here you can see the two together. Right? Nothing mind-blowing there, just something I like pointing out as we build all of these connections. Okay. One last thing I want to talk about, and that's functions of three variables, because there's a constraint here all of a sudden. So it takes three coordinates to determine a temperature in space. The x, y, and z would be the location in space. The output would be the temperature. So this would be a function of three variables. Now think about this. A function of two variables creates a plot in 3D. Then a function of three variables puts us into 4D. So we cannot plot a function of three variables. We can't. There's no visual representation. So a lot of what we're going to do in here is going to involve function of two variables, because we're going to spend a lot of time looking at the geometric properties. That said, right, that's, thanks, Cooper. That said, you know, all the stuff we're going to do with the functions of two variables applies to functions of three variables, four variables, five variables. That's why we're going to do it with functions of two variables, but everything we do extends. So what happens in this case, we can't plot this. We couldn't plot this as a function. We have too many variables, too many dimensions. So, but if we think about all the places where the temperature is 1 degree, what that does create is a sphere of radius 1. That becomes something we can plot. And if you want to plot something like this on a 3D plotter, this is what's called an implicit surface, because it's not equal to any particular variable. And you can see the x, y, and z all sit on the same side. And there's our sphere of radius 1. Okay, not a function of two variables like we talked about, wouldn't pass the vertical line test. This is what we call a level surface. All right. It's analogous to the level curves we were just talking about, except what we get is level surfaces. And so every time we change our output, we get a different level surface. So we can see the level surfaces of this function are spheres that get larger as we increase the output. Now, we're not going to do a whole bunch with level surfaces. There is going to be a couple cool things that I'm going to show you in the next couple of weeks where we leverage level surfaces to make some formulas a little easier. But most of the time, we're not going to be worried about trying to figure out what all the level surfaces of a function of three variables look like. It doesn't give us any, the geometrical view doesn't give us a whole lot of information. But there are going to be uses of level surfaces when we start talking about tangent planes and normal vectors. And that's one of the reasons I bring them up. The other reason is just to introduce you to the term. When we have a function of 3 variables, our inputs are ordered triples. So our inputs are actually a point in 3 space, and then there's something going on at that point 3 space. Temperature, as Cooper pointed out, it could be the smell or the strength of a smell in 3 space. We can't graph them because they don't have a 4th dimension, but we can graph the level surfaces if we want to get an idea of what's going on. So, this was from our temperature function. So every point on this sphere is at the same temperature. So what we do is we let the output, oh, absolutely, yeah. Smell being that 4th dimension, right? That could be the output of our function. Absolutely. What we do is we set the output of the function of 3 variables to be constants, and that makes something we can plot as an implicit surface in 3 space. These can get messy. We're going to stick, most of the ones I'm going to give you will have stuff that we can identify. And one of the things you're going to practice today, because what I'm going to do now is give you guys the 13.1 worksheet, let you guys work on it for the next 30 or 40 minutes, because we're not going to spend that long on 13.2 today. But what I want you to do in the 13.1 worksheet is just get a little bit of practice with contour lines and 3D plots. All right, so I put the 13.1 worksheet into chat. So you got a link to it there. And so what I'm going to do now is I'm going to break you guys up into groups. There's 3 problems on here. And the answer key is on the 2nd page, as always. Try to do the 3, yeah, it's at the top of chat. Not everybody might be able to see it. So let's put it back in. And guys, all the worksheets and the PowerPoints are always linked in more as well. So you guys always have them. Let's see, sorry. All right, and I'll send it out once you guys are in groups too. What I want you to do is try and do the 3 problems without looking at the answer key and using the answer key to check your answers, especially for number 3, because it's just a matching problem. If f of x, y does not pass the vertical line test, it's not called a function. Because f of x, y, to be a function in rectangular, must have a unique input, must have a unique output for any input. And so if it did not pass the vertical line test, what we would have wouldn't be a function. Now we're, if we look at a function of 3 variables, things change, because this would be a function of 3 variables because each input does have a unique output. But there's no vertical line test for this. Remember that the vertical line test is just a visual tool to help understand the definition of a function. So we can use it with functions of 1 variable and functions of 2 variables. After that, the vertical line test loses any meaning because we start to move, as we talked about earlier, into 4D. But the idea or the definition of a function remains, and that is each input must yield a unique output. And the way we can tell that is if we put in an XYZ ordered triple, we get 1 and only 1 output. It's not like if we put, if we put in the point here, what's a good point? 1, 1, it's going to be up here like rad 2, rad 2 over 2, I think. That only produces that single point right there. It's not going to be like, oh, it's this point or it's this point. So it's more just about getting that idea of just having that unique output for a given input. All right, guys, I want to get you started on this worksheet. Like I said, we're going to, let's see, it's 5:40 now. So about a half hour, 35 minutes, I think. If you guys get it done early, just let me know. You'll have the answer key. Let me get you.
Oh, okay.
All right, welcome back. Great job today, guys. Don't forget to post your solutions for 13.1, sometime before next class. Now, one thing we're going to finish with today is limits and continuity in functions of 3D. Kind of a smaller topic, but there's a couple things I want to point out. We'll look at maybe one or two problems depending on how much time we have. So limits of a function of two variables work very similarly to functions of one variable. All right. What we're trying to do is figure out if we get really close to some ordered pair, does the function approach a value? In 2D, we were looking to see as we got close to an x value, as we got close to an input, did our outputs get close to a value? It didn't have to exist at that value. Now, if the function does exist to that value, that's when we have continuity at that point. All right. So I just want to show you a couple of things. And so I'm going to bring over the worksheet because we're not going to have time for it today because I want to take last few minutes just to show you guys a couple other things. But let's just look at this worksheet here. Let me zoom in so you guys can see it. There. All right, so for number one, we're using this, this graph over here. So I want to talk a little bit about this because I do think graphically is a good way to start to talk about limits. So our goal is to say, okay, well, as we get close to a point, does our function exist? So let's just take A here. As xy approaches 1, 2, what is the limit? Well, here's our x, and as we go, and here's our y, so as we go towards 1 in the x and 2 in the y, we end up right here. So that would be our spot in the xy plane. Now we have a level curve going through there at that point, and we see that the value of that level curve is 3. So the value of this limit would be 3. So, because we're getting sufficiently close to that z value as we go towards 2 in the y direction and 1 in the x direction. So it's very similar to what you guys did in Calc 1, except, instead of coming in from both sides, we're coming in from, all 4 directions. And like I said, the point doesn't have to exist. So for example, let's see here, as we're going towards 2, 1 in the y, the function has a hole there, but that's okay because we're looking for a limit. So we check out the value of that level curve, which is 4. So that limit would be 4. All right, so that's just to give you kind of a graphical sense of what's going on with these limits. All right. Now, let's talk about if we're given a function. All right, how do we deal with that? And I'm going to do number 4 here. Now, first off, I should say this, before I do any of them, first thing you always do with a limit, and this goes all the way back to Calc 1, you try plugging in the value. So number 2 here, if we plug in 0, 0, so all the x's and all the y's end up zeros. So 0 plus 0 minus 5 over 2 minus 0. Whoa, that's not supposed to happen. This limit here is just -5/2. So that's always the first thing you do is you plug it in and see what you get, okay? So let's talk about number 4, where if we plug in 0, 0, notice what happens. We get sine of 0, which is 0, over 0. If you remember from Calc 1, this is what we call an indeterminate form. That means it may or may not exist. We have more work to do. Now, if you plug in the 2 numbers and you get 0 over a number, the limit is 0. If you plug in the two numbers and you get a number over 0, the limit is undefined. It's very straightforward. So it's really only the 0 over 0 case where we start to get interested and say, hey, we got to do more work. So what's that going to involve? Well, we know we've got an indeterminate form. So the first thing I would recommend is plotting it. All right. So if we take a look at the plot, we want to look at what's going on at 0, 0. Notice how the curve is nice and smooth. We're going to expect that limit to exist. L'Hopital's is still, and L'Hopital's rule is still game for these. It's just we won't do it with multivariable. I'll show you how L'Hopital's will come in on something like this. So it looks pretty smooth right here at 0, 0. So even though the function may not be defined at 0, 0 because it's got a hole, we're going to expect that limit to exist. So here's how we can evaluate a limit. And you saw this in the videos, but we do it along paths. And so the most common paths, and we're going to do just a couple of these just to kind of get you acclimated. The most common paths are, actually, let me just go ahead and bring up the whiteboard. That'll be easier. The most common paths are x equals 0, y equals 0, x equals y, and x equals, or y equals x, y equals negative x. So let's just do a couple of them. For instance, we look along the path x equals 0. It's kind of like doing when we're looking at the plots and looking at cross sections. So if x equals 0, this thing simplifies down to the limit as y approaches 0 of sine of y squared over y squared. This again is a 0 over 0. Now we can apply L'Hopital's rule. Now, as a reminder, what L'Hopital's rule does is it allows you to take the derivatives of the numerator and denominator separately and recalculate the limit. So derivative here is going to be a product rule. So we have cosine of y squared times the derivative of the inside, so times 2y over the derivative of y squared, which is 2y. Those cancel. Now plugging in 0 gives us cosine of 0 or 1. If we go back to our graph, that seems to match. That means we're going along the path where x equals 0, so we're going along this path right here. That seems to fit with what we're seeing graphically. We'll just do one more path for today. But you can do, the thing is there's infinitely many paths. That's why we have to check at least a few and check graphically. Based on the graph, we already expecting this limit to exist. We're just kind of verifying it. So let's say we check the path y equals negative x. That means we're plugging in negative x's for all of our y's. And this just becomes x going to 0. So we end up with sine of x squared plus negative x squared over x squared plus negative x squared. Now the negative x squareds become positive x squareds. So we end up, oops, sorry, got to write the limit up front. We end up with limit as x goes to 0 of sine of 2x squared over 2x squared. Now, all I'm doing is rewriting the limit. I'm just simplifying. I didn't take L'Hopital's rule here. What I do when I take L'Hopital's rule, I like to put an h over the equals so that if anybody comes back to look at my work, they know to get from this step to this step, I did L'Hopital's rule. Plugging in 0, once again, 0 over 0 case. This one actually works out pretty similar to the one above. And you're going to find any path you do is going to come out similar. You know, we're going to have cosine of 2x squared times 4x over 4x. There's our cancel. And once again, we get 1. Those are coming out to be the same. So what it's doing is it's verifying what we were seeing graphically. All right. So that's if a limit exists. Let's do one where it doesn't for a little bit of contrast. Number 5 here. And just like when I post the videos, I'll post these whiteboards as well. Yeah. Yes. So the question that came up is, checking on multiple paths. Yes, because the thing is, there's infinitely many paths that we could actually come up with. Again, the most common are x and y equals 0 and y equals x and y equals negative x. Y equals x squared is a common path. So that's why we're actually using a couple of paths along with the plot to verify it, because it's really infinitely many paths. And we're not going to get into like the formal proof of it, because that gets a little long and a little away from what we're trying to do with this. But just be aware that what we do is we check along multiple paths after looking at the curve. Once we see that smooth nature, we expect it to exist. So we just do 2 or 3 paths to confirm it. Let's do one where it doesn't, number 5 here. So first off, let's look at the plot like we just did. So we're going to plot 2xy over x squared plus y squared. And we're looking for the limit at 0, 0. Look at the mess that's going on at 0, 0. We'll even zoom in on that a little. Look at, the more I zoom in, look at what's going on at 0, 0, right? The function kind of blows up there. We're expecting that messiness to mean that the limit's not going to exist. So what we're going to do is choose 2 paths to verify it. So let's do that. Let's do y equals x. That's a nice, easy path. So basically, if they're equal, they're going to the same thing. So x equals, goes to 0 of 2x over x squared plus x squared. So this would be sorry, getting a little ahead of myself. This would be, let's simplify the limit as x approaches 0 of 2x squared over 2x squared. That completely simplifies down to 1. The limit of a constant is a constant. So that just ends up equaling 1. Now if we try the path y equals negative x, we got the limit as x approaches 0, because x and y are the same. Or if x is going to 0, negative x is going to 0. 2x times negative x over x squared plus negative x squared. So this time, might already see what's going to happen, because on top, we're going to end up with a negative 2x squared. The bottom works out pretty much the same. And that comes out to positive 1. So that comes out to negative 1. I'm sorry, I even said positive 1. That comes out to negative 1. That is not equal to what we got in the other direction. So this is a DNE. If any 2 paths that you choose are not equal, then we're guaranteed that the limit doesn't exist. All right. So I wanted you to see a couple of examples of those before you get into the homework on them, even though we didn't have a chance to get into the worksheet on 13.2. It's not a really long section. They don't cancel in the denominator, because the negative x times negative x is a positive x squared. Let's put this in parentheses. Because what we're doing is we're replacing y with negative x, then it's being then it's being squared. Order of operations, we're basically multiplying a negative times a negative.
So I'm a little confused because in the denominator for number 5, it says x squared plus y squared.
Mhm.
So if y was equal to negative x, wouldn't it just be x squared plus negative x squared?
But the negative x is what's being
yeah.
squared.
After you square them. Yep, never mind.
It's just order of operations, yeah.
Yep.
And, guys, always be careful how you put these in a calculator, because if you put it in a calculator, negative x squared, it will read the negative on the outside. That's different than this, okay? But because we're replacing the y squared and the y is y times y, then when we replace that with the negative x, it's basically replacing each of those y's with a negative x. All right. So I wanted to have a chance. Yes, exactly, Ryan. If the limits contradict each other from different paths, it's automatically DNE, and it's any two paths. They have to be the same from all paths in order for the limit to exist. Okay. I wanted, like I said, I wanted to go through that. I didn't want to spend a lot of time on this section. It's not going to be a big section for us, but you're going to do some limits in the homework, and I just wanted you to see it, have an opportunity to see a couple. All right, there's one last thing I want to talk about, and I know we only got a couple minutes left. I'll try not to go too much over. Last thing I want to mention is a couple things about the take-home problems, just because a couple questions have come up. And I just want to make sure I point these out. Everything I'm telling you is documented in the midterm take-home problem folder, but I just want to make sure I reiterate it, and if you guys have any questions. The first thing is, you have access to the take-home problems for Module 1 and Module 2. You'll be getting the take-home problem for Module 3 next week, all right? And those are not due until the midterm, which, don't quote me on this, is like March 14th or 15th. It's in the Moore calendar, but it's still a few weeks away. That's when they're due. If you want to turn them in early, that's fine. Just make sure you follow the submission guidelines that are in the folder. And basically, those submission guidelines are to have the problems done in order. So, if there's a module that has multiple take-home problems, make sure you do the problems in order, and your submission should be as a single PDF, okay? Now, my requirements for the take-home problems are that they're done in order, submitted as a single PDF, and turned in on time, and that you justify your work. Those are really my only requirements. You can use any programs you find useful to help you solve the problems. In here, we have used Wolfram Alpha, okay? I just happened to have this open earlier, so I just wanted to bring it over. If you do your problem in Wolfram Alpha, take a screenshot of your work, so if I were doing this, I would do a screenshot of what I entered and what my result was. And I would input that as part of my solution. If you do it by hand, you can take a picture of your handwork. And what I would recommend is pasting it into a Word document. That way you can keep everything in order. And at the end, you can save it as a PDF. Oh, and don't forget to put your name in the file name of the PDF, because if you don't have names on your work, I can't always distinguish whose is whose. So always put your name not only on the file in the file itself, but on the file name. So by all means, you guys can use any, Wolfram Alpha. You can use, if you guys haven't seen this one, this guy here is called Symbolab. All right, you can use Symbolab. Same thing. You just cut and paste what you did. For those of you guys who are familiar with MATLAB, you can use MATLAB. You have access to Maple. There is information on how to use Maple in the folder. Guys, none of these are required. These are just options. I don't have any issue with any program you decide to use. If you have old versions of Mathematica and you want to use those, totally fine. And again, you do not have to use technology to solve the problem. If you solve it by hand, just take a picture of your handwork and put that into the Word doc. You can type up anything in the Word doc as part of your solution. The last thing I do want to mention is any plots. So if the problem requires plots, if it's like include a plot of the tangent plane or something, plots must be done in a 3D plotting program. I will not give credit for hand-drawn plots. We've been using the Calc 3D plotter in here, so that one's perfectly fine. But again, you're not required to use that one. Maple can do 3D plots. MATLAB can do 3D plots. Desmos is fine. GeoGebra is fine. You guys can use whatever program helps you solve the problem, okay? Again, all I care about is that your work is justified and that any plots are done in some kind of 3D plotting program. Any questions about that? Any general questions about the take-home problems?
Well, is there like extra credit for doing it by hand if it's like a problem?
No extra credit for doing it by hand on those.
Okay.
And guys, I not only can you use technology, guys, I encourage you to use technology on the take-home problems. The take-home problems are problems that would be too long to do in a testing environment. But they're good problems over the topics we're doing. And a lot of them, the work is in setting them up. So I don't want you to be bogged down. We've talked, the last section, we talked about some of those arc length problems or some of those, curvature problems, right? Doing those by hand can be a lot of work. Don't kill yourself doing a curvature problem by hand if you don't want to. Feel free to use Wolfram Alpha or Symbolab or something to do all the heavy computations for you. That is part of the point of the take-home problems, is to allow you to use the resources you feel comfortable with. Again, if you want to do it by hand, great. Maybe check your answers with technology, because I want you to do well on the take-home problems, but they are take-home problems. So I expect to see the justifications for what you did and expect them to be done well, okay? So the question came up, what if you do the calculations right, but the answer comes out wrong on the midterm and final? So the answers on the midterm, now this isn't for every single problem, but the answers on the midterms and finals are taken from common errors on those problems. So to Ryan's point, let's say you're doing a cross product and you mess up the sign on the middle component, right? That will be a possible answer, and you would get partial credit for that, even though it's multiple choice. All right. So maybe A is the correct answer, that's full credit. B is the one that has the wrong sign that's done most often, and you did that one, you'll get partial credit on that. So there is opportunities for partial credit in those cases, where if you make just a small common error somewhere along your solving, you can still get credit. Also, and we'll talk more about this as the final gets closer. There's 40 questions on the final, or midterm or something like. It's somewhere around 40, but there's not 40 problems. There's much less problems than that. It's problems that have been broken down into parts. So part A might be setting the problem up. Part B may be solving it. So you could set the problem up correctly, and then if you make an error in your computation, you might only get partial credit on the second part, okay? So that has all been built in to that exam. And also to that point, That's more reason for you guys to show justification on your take-home problems. Because if all you give me is an answer and it's wrong, I cannot give you any credit, all right? Now, if you give me an answer and it's right and there's no justification, I will only give partial credit. But if I can see what you did and maybe you entered something wrong into Wolfram Alpha and I'm like, oh, you know what, all they did was put in the vector wrong and that's why their answer came out wrong. I'm able to give partial credit for that. If I don't see your work, I'm not able to. So it's actually to your advantage on the take-home problems to show how you got to the solution that you got to. Okay. Sorry, guys. So much for not going over. But other questions about, this is a good time for this. You know, if you got questions about, we'll talk more about the midterm. What the midterm review is going to be up either tomorrow or Saturday and more. So let's not talk about the midterm anymore till you have a chance to look at that. And maybe next week or the week after, on a day where we're not as busy, we'll start to talk about the midterm a little more. But because we're talking about the take-home problems, if you got any questions about the take-home problems, let me know. Otherwise, you know, sorry I kept you over again. I'll let you get going. Good job today. I'll get the recording of today's lesson up. And yeah, don't forget to post your solutions from 13.1. So if you have other questions, feel free to answer. Oh gosh, guys, sorry. If you got other questions, feel free to ask. But otherwise, you know, feel free to get going too. I know it's late.
Yeah, I was going to see if I can get some help with one of the homework problems, 12.3.
Okay, we can take a look.
Because, yeah, I'm not sure why this is the second version of the problem, and I thought it was going to be easier because it had X as a positive instead of as a negative, because when I would try to calculate, I'll give you the one that I have. Am I able to?
Yeah, give me 1 second. I want to